Good morning, everyone, and thank you all for joining us for the second session of our Plastics 101 series. It is a four-part series. This is part two of that series. Thank you all for
Good morning, everyone, and
thank you all for joining us in these, trying testing times. I know this is quite unusual for a lot of us here. Um, Hopefully, you're all staying safe. Hopefully, you're all following the advice and the guidance that we're all getting to stay indoors.
Echo that, Nikhil. Strange times indeed, and straight out of a movie. But yeah, hopefully everyone's safe and sound and listening to the advice.
Yep, absolutely. By the way, my name is Nikhil Venkat. I am an application engineer here at Kativ, and the other voice that you just heard was Brian Pelly. He is the MoFlow technical specialist at Autodesk, and hopefully, I didn't butcher your job title, Brian.
Yep, I've been called worse, Nikhil.
So before we jump into the content for today, one of the things that I wanted to mention was, like I said, we're not quite used to uh, the, this remote working all the time. So what we have done here at Kativa is put together this resources page about working remotely, where you'll see some information about how you can kind of work remotely. Here's a webinar that we did fairly recently, and this was about last week on remote work and how you can use the tools that you already have in as part of your Autodesk software to work remotely. And there are some extended access programs as well. So I'm going to go ahead and post this link in the chat window, and you can all go ahead and access it. Now, Brian, do you want to jump in and talk about the extension?
Oh yeah. As an effort to this large wave of folks now working from home, which has created a lot of interesting dynamics in online meetings. Um, Autodesk has offered free access to cloud collaboration tools such as Fusion 360 and Fusion Teams to help kind of manage sharing and collaboration of data. So if you're not familiar with Fusion 360, it does usually come entitled with Moleflow and our other advanced manufacturing products, but this is something we're just offering regardless of who you are, where you are.
Yep, exactly. Absolutely. So you'll find a lot of information on this page. Feel free to check this out. I just put this in the chat window. All right, let's go back to the real reason we're here, I suppose. Plastics 101. So why are we here today again? If you didn't join us on the last session, you can find that up on YouTube. It is posted. So I think we can definitely help you out, direct you to that link. But again, we're here to help you guys, our partners, all of you, be more successful, more competitive in your business through with guidance, with technology, with support, and essentially, we're here as an extended arm for you guys to lean on. Now, Kativ is one of a few Moleflow specialized partners, Autodesk Moleflow specialized partners. What that means is we have been certified by Autodesk to actually train you guys and certified as experts um, to support you with your usage and your adoption of Moleflow. Now, last time around, the big thing that we talked about really was what it takes and how do you do it right the first time, right? So how do you, for example, understand the intricacies of molding before you even start any physical processes, right? So we talked about the four key pillars of plastics design. We talked about exploration of those four pillars, and we also talked a little bit about materials as well. Now, the reason we've structured it this way, we're going to touch on each of these individual pieces, individual pillars, if you like, over and over again, but they're all going to fall under this broad, each of these broad umbrellas.
Yeah, it's amazing to me. I spent, 4 years in school and then a lifetime trying to understand and manage the complexity of those four key pillars: material, process, part design, mold design. Whether you're a community trying to optimize your plastic components or an individual, the more you know and explore these key variables, key components, the better decisions you're going to make. And that's the manual approach, whether it be community or individual. In Fusion 360, there's a service called generative design. And, just as an example of how much content there is around those four key pillars, we kind of spilled over last session and didn't really get to talk too much about what I like to call man versus machine, right? So,
Okay, it appears we have lost Brian's audio there. So I'm just gonna jump in here.
okay. Can you
Brian?
not hear me, Nikhil?
I can hear you now.
Okay. So maybe give me a check on what you last heard.
You were talking about you were talking about Fusion 360 having this
Yeah. Okay.
technology in here.
Yeah. So it's what I've termed, is like man versus machine. It's like all these things we need to know and to making good decisions for plastic components. We've kind of opened up that artificial intelligence with generative design. So applying solve a problem to the computer, giving maybe some areas that we want to preserve, a space we want to live in, obstacles that we need to avoid, and then allowing the software to run not just an FEA analysis, but also shape generation based on the process type. And these are two examples in the design for manufacturability of that process type and the subset of materials. So a full exploration of these four, kind of key variables is where we're headed. And, for those of you out there, afraid of technology, this is not going to take our jobs just yet. The machine isn't going to take over just yet, but it does augment our decision process. It gives us geometries that we would have never explored, hundreds of geometries that we can kind of pick from, where you look at the classic approach where you get shaped surfaces from ID, you get a mechanical designer, and then an FEA reliability analyst that all kind of work together to get to a point where then you pass it to, say, a molding plastics engineer for their 2 cents on DFM. So the more we can kind of do this up front with tools like this, the more choices, good choices we're going to have in the future. And we're going to see this trend more and more. So it's not going to go away. I don't think it's going to take our jobs either. I think it's going to be a good augmentation of our workflows and make us more efficient.
Absolutely, absolutely. Now, part of why it's not going to take our jobs really is because some of these designs, as you can see, they're so complex. There's so much going on here. There's no way you can sit down and design, or you would sit down and design this and actually create prototypes for each of these to figure out what's going on in there. And so we use simulation, right? We do this beforehand on a software of some kind and understand what's going to happen, understand the process, so it's a little more predictable, so we know what might go on, etc. Now, specifically here, we're talking about injection molding simulation. So I get this question a lot. I'm sure you do as well, Brian. What is injection molding simulation? What is it? Because we're on the on the shop floor doing, creating prototypes, understanding what's going on there. What is simulation? Well, there's several ways you can define simulation. The first one is, of course, it is technology that answers some basic questions about plastic manufacturing, right? So, is it going to fill? Where will you see these defects? What's the best gate location to use? Um, is the runner system balanced? Is this the best part geometry, or is this what's going to make it most manufacturable, or do we need to make some changes? You can also define it as a piece of technology that would predict and avoid beforehand manufacturing defects. You can also, depending on who you're talking to, define it as technology that'll help optimize the part design and mold design for manufacturing, right? So it'll help you minimize cycle time, help you become more efficient, help you become a lot more productive as an organization, etc. Well, my favorite one really is it is an opportunity to save money, right? This is something that resonates with most people. If you're talking to your managers, talking to your president, director, whoever that may be, they are probably aware that a lot of the molds that are being created have to be constantly retooled. They have to be constantly um, checked and tested for their cooling efficiency and uh, whether or not there's a better way to produce them. That's happening over and over again, and they're probably aware of that. Some of these design considerations, making them upfront, will potentially lead to massive savings uh, down the road. So simulation will definitely is a great starting point for this innovation. Now, I know when we say simulation, we typically think about finite element analysis. We think about the bending of a beam or something like that, right? Something fairly simple. Now, whether you're using a structural simulation solution like Nastran or ANSYS or Abacus or anything else out there really, and you go ahead and run an FEA on a simple part like this that you see on the left, it's going to give you some areas that are safe. It's going to give you some areas that may be slightly critical. It'll tell you what the safety factor is, etc. Now, the one advantage that something like Moldflow has, Moldflow is of course an injection molding simulation software, is it will allow you to simulate the process of filling and packing and cooling and warping, etc. But what it'll also do is allow you to understand what defects arise from that molding process and how those defects actually help or actually affect the strength and stiffness of a certain material. So in this case, for example, we see that there are certain areas, but if you compare the two FEA images here, the one on top gives you some rough areas of maybe slight concern, but depending on the color code, red is of course most dangerous. Um, Depending on that, you can see that there are certain areas where you've almost got some kind of crack propagation there, but in the picture at the bottom there. So that's what it's giving you. It's giving you these as manufactured, as molded um, effects, and it's giving you it's quantifying that strength and qualifying that strength, as opposed to standard FEA where you're designing or where you're running FEA based off of what you've designed in CAD, right? So what you see on your CAD screen is not necessarily, well, not necessarily, but it's never what you'll eventually get in your hand as a physical part, right? The physical part always has some defects, some imperfections, etc.
Yep, just got to look close enough. Yeah, some of these artifacts like weld lines have a strong signal to where you might run an FEA with a perfect CAD model and it looks great, where it's actually, in this case, an example where it fails differently along the weld line in other areas, things like residual stress or orientation effects, especially with composites like fiber filled material. So a lot of dynamics that we can add and leverage the material database in Moldflow, but also passing the as molded data, residual stress, final shape, um, orientation of fibers onto FEA, so we get more accurate, uh, virtually mold it, virtually try to break it.
Yep, absolutely. And you touched on a few different things there, Brian. Um, Essentially, what you were talking about was the different things, the different areas that Moldflow um, can actually help with, right? Injection molding simulation can actually help with. So, for example, if you're doing R&D and you're not quite sure what the best approach is, well, Moldflow will help you with process exploration, creating intellectual property. If you sort of need to get a little creative with your process, it helps affect, or it affects part design engineering. So whether something is manufacturable, moldable, whether it's going to actually remain strong enough that it's going to that you can predict, right? Similarly, if you're developing molds, we talked about how expensive molds could be. So how's the cooling? How's the venting? We talked about again last time. If you look in the chat window, there should be a link for the last session. One of the things we talked about was what is a bad mold, right? How do you define a bad mold? Well, the answer is if you don't get the part that you're looking for out of the mold, that by definition would be a bad mold. So this will help you understand all the factors, all the variables that go into mold design or development, and also your process development. So what are the different parameters that are going to affect your process, right? So whether it's the injection pressure, the mold temperature, the melt temperature, whatever that may be, this process development portion of it through Moldflow will help you understand which variable affects the entire process the most, and then you can kind of zero in on that and try to modify that to really understand what that sweet spot is.
Yeah, it's a good example of like the evolution of details. Early on, you don't have a lot, but you can certainly digitize it or present it like the as molded data early on when you're doing reliability testing. And some of the key things there is, from what I've seen, is that 80% of a lot of your root cause to the issues, is defined by some early decisions during the design process. So the geometry that you're creating for this component, the material selection process has a big impact, and then where you can and can't gate it. So not to say that you can't create other issues downstream here with a bad mold design, bad feed system, or cooling, or bad process. Certainly can. A lot of times, though, it's aggravating those three big variables: geometry, material, and potential gate locations.
Absolutely. So again, part of what you said was the materials, right? So typically inside the industry, we get a lot of, especially with material specialists, there's a lot of different things um, that they tell us, right? So how do you kind of zero in on the best material? Where do you find that information? Product development costs keep tending to escalate and increase due to material related issues. So again, as Brian said, a lot of these things, a lot of these factors, you kind of need to consider beforehand before you start um, putting a shovel in the ground, so to speak. Now, one way of doing that, of course, if you have Moldflow, if you already own it, then there is this massive material database in there that has so much information that it's sometimes hard to digest.
We're spoiled, Nikhil. If you go back in
Absolutely.
time, yeah, when I've looked at like other programs, FEA specifically, there's been so little material data where Moflow would just expect and to have all this data at our fingertips, things like design of experiments, data on shrinkage. So literally DOEs on shrinkage and things of that nature. Very spoiled.
Yep, definitely. Well, I guess now folks that have ANSYS are going to be spoiled as well, because ANSYS quite recently, not sure how long ago, probably 3 4 months, they purchased a company called Granta, and ANSYS now has this software called called Granta Selector. Right, essentially, it is this massive encyclopedia of materials data, which allows you to compare different materials. It doesn't even have to be different materials of the same class. You can compare like a plastic against a metal against an alloy, and try to do this apples to apples comparison of whether it's strength, whether it's stiffness or cost or availability or whatever it may be. Right, it allows you to make those smart materials choices uh, well beforehand. So yeah, for those of you that have Molflow, those of you that have ANSYS, you do have access to these massive materials databases, and if you have both, then wow, you have a lot more materials than you're ever going to use. So, and you've also got different in each of these. You've got different grades of materials. You've got different manufacturers, etc. All right, so this is actually some of the most fun part of any webinar, right? It's a great way to understand exactly what all of you are looking for, and kind of what you do on a regular basis, right? So we have a series of poll questions here. I'll give you a minute or so to answer them. The first one, I'm going to launch this now. Hang on. Okay, so you should be able to see the poll going on there. You should be able to see it on your screen. The first one is, do you use any simulation tools for FEA or CFD or injection molding at the moment? And if you do, then the second question is, for what purpose? And of course, what simulation tool you use, right? Whether that's an Autodesk tool, whether it's an ANSYS program or SolidWorks program or something else. So I'll just give you guys a minute or so to answer this. It's nothing crazy. Brian, in your time, your experience, do you go back and forth a lot between different programs, say FEA, CFD, Multiflow? Do you do a lot of that jumping around?
I have in past lives. I've one of my last jobs I bounced around Moldflow, CFD, and simulation mechanical at the time pre Nastran. It was investment casting industry, kind of like geared towards metals. Interesting process and very intricate as far as how many steps there are, and the opportunities to apply simulation was very it was rewarding, kind of a candy store for engineers, because
Mhm.
there was so many different processes that went into forming a investment casted component, and the cost of them are so high.
Yep,
You really could save the company a lot of money by applying these different technologies.
absolutely.
Yeah, my first shot at like just tallying up it was hundreds of thousands within the first year. Modeling investment casting, modeling the patterns that we injection molded, doing CFD analyses on how we cool the investment castings. I mean, we're talking well over $1 million by my second year there. And so, yeah,
Wow.
I think there's always, the potential, and it really depends on, your company, what do you do, and where you can apply some of these technologies.
Absolutely. Yeah. The cost savings usually tend to snowball, just like the cost of mistakes tend to do, right? So
Exactly. And that's the key. If you have a good handle on what these things are costing you, then people are very incentivized to invest in some of these technologies and the manpower involved. Literally, I could go to a production manager and say, you're losing $15,000 a week on this particular application, and I know how to solve it. It's like, do you want to keep paying that, or do you want to, spend some of my time on this problem and to make it either reduce the cost in the case of like scrap rate, or in some cases, we just were able to make it go away. So those bottom line discussions
yeah.
when it comes to cost savings is quite interesting. Depending on the folks you're talking to, accountants seem to think a little bit differently than a lot of us. So there are also some interesting conversations around cost savings.
Great. Okay, so I think we have a lot of polls in. Interesting. I'm going to go ahead and end this now, but we do have a pretty interesting mix here. A lot of about half of you do use FEA tools or simulation tools already, which is great. What I do see here is that a large number of you are front end design tool users, right? So you're kind of, if you're front end design um, simulation users, then it's in terms of mold flow, relating that to mold flow, you're probably looking at using something like Advisor. Um, yeah, but this is great information, and for the folks that are using ANSYS at the moment, absolutely, uh, try and get some more information about Granta, and if you would like some more information, then of course feel free to reach out to us. We can point you in the right direction. Now, we've got a couple of really interesting case studies here, Brian. If you want to run through them real quick.
Sure. These are, just basic examples of what happens when you start thinking about using tools to optimize up front. Something as simple, casual environment as MoFlow Advisor was applied to these two housings to simply, reduce wall thickness without impacting, processing. And you can see in the bottom in red that the savings are significant. Savings can be looked at a couple of different ways, but the low-lying fruits usually a high volume part or an expensive material or a very large like run rate, a large machine. Those are generally where I've focused in the past. What's the biggest bang for my buck? What's the low lying fruit? And then expand going after the tougher ones later. And there's a couple other examples here, but basically, you know, being able to balance things, and that's kind of some of the subject matter that we'll get into in the next couple sessions as far as mold design, mold layouts, process optimization. But running, family molds, hopefully you don't have to do that, but it's tricky. And if you're not filling things at the same time, basically the bottom line is if you're not delivering same melt, temperature, pressures, shear rates, or stress velocities, you're going to get different physical properties and cosmetics, which is always this tug of war in these. So balancing it here, you can see saves a good amount of money as well as some of these more complex parts, looking at this up front to determine, what the ideal gate location. I can't count how many times I've seen gate locations driven by where you can't see it. So a non-cosmetic area, or based on the economics of what you think the tooling type should be. And we'll get into that, I think, next week's subject. But those decisions are made based on economics, but what's the cost of getting a part that you can't use or doesn't perform? And so this is a good example of that upfront stuff that we can look at, and some more difficult, consequences or details like core shift. So how is that going to affect functionality, shape, say roundness or straightness of a through hole? And these are all things that we can explore early before we're locked in to that decision we make on gate location, tool type. Um, okay, I think that's all we got for cost savings examples.
Yeah, definitely. But part of that is also knowing what you're looking for to begin with, right? Understanding what you should be focusing on. What are the different areas that you need to shine a light on to actually make sure you get this cost savings advantage, right? You don't want to do an incomplete simulation and then run to the shop floor, make your prototype, make your mold, and then you realize there's some issue um, with
Yep.
the cooling or something like that. So
Absolutely. There's a sequence and kind of workflows, and if you kind of look at the conception of Moleflow early on, it really was based on design principles, theories that we can apply and that are quite well documented as far as what is good, what is bad. Um, Good lead
absolutely,
into this, yeah.
absolutely, yeah, that's a great segue into the actual Moleflow design principles. What you see here, by the way, is a um, fairly legendary, I think it's fair to call it, uh, textbook, reference book for plastics engineers, Moleflow Design Guide by Jay Shoemaker. And most of the time when you're looking for Moleflow reference material, this is the first thing that pops up. So just FYI. One of those things that they talk about in the book is one of the most basic things is uniform wall thickness, right? First rule of plastic part design is that you would like to have uniform wall thickness. That also happens to be the first rule that's usually broken. So this is the thickness value across the majority of the part. Of course, it's not as if you're not allowed to have any areas are that are different. But what we're trying to call uniform here is basically try and avoid these massive changes in thickness that are sudden, right? If there are going to be changes in thickness, make it small, make it subtle, make it gradual. And if there are going to be large changes in thickness, then maybe we need a different approach to mold that part, right? And we'll run through these fairly quickly. If you would like to talk about any of these in detail, if you're seeing issues with any of these, feel free to reach out to us. But just in the interest of time, we're gonna run through this fairly quickly, and this isn't ridiculously complex either.
Yeah,
Um,
think that wall thickness is an interesting guideline, because as you pointed out, we then apply draft, which then
mhm,
breaks that guideline. And I guess one thing to keep in mind is guidelines are always broke. It's just a matter of how severe we can get away with breaking them, and that's truly where like simulation comes in, to kind of be that referee, if you will. It's like, how extreme can we go past this guideline before we get into troubled waters, if you will. So there's a lot of things like draft and undercut and design principles that are meant as guidelines, and we know, we've molded all the easy stuff. Now we see more and more difficult stuff, and we see these guidelines broke constantly. And how do you judge that? It's truly where simulation shines.
That's a great way to put it. Simulation as a referee. I'm definitely going to use that in the future.
Well, I got no football or hockey to watch anymore right now, except reruns. So
All right.
it's on my mind.
It's on your mind all the time.
Yeah.
Okay. Um, like you said, right? So simulation is something that will help you understand these things beforehand, and sometimes it also helps you understand things that you simply don't see in a physical part, right? So you can look at the effects of it and trace it back to the cause, but why do that when you can directly look at what's happening, right? So for one of those things is a controlled and unidirectional flow pattern. So these basically what you're hoping for is orientation in one single direction for one single um, portion of the part, I suppose. And if you have flow in all kinds of different directions, right? You see the first set of images there. That's going to lead to high stresses, to unpredictable warpage, to unpredictable shrinkage, to potentially even cooling issues, right? So that this is another thing to consider, just as gate location selection is. So depending on whether you have advisor or insight, actually no, not depending on, but regardless of whether you have advisor or insight, you do have the ability to one select up to 10 gates, and also second, have the software tell you where the best gate location should be, right? You can also say, yeah, in this particular part of the geometry, it's going to be fixed to something else, so I don't want any gate location in there. um, I want that entire region to be gate free and move the injection location elsewhere. So you've got the ability to do all of that, and this will help you kind of visualize how the entire mold is going to get filled depending on the gates, the injection location that has been selected, right? So whether that's one injection location, whether that's two, three, four, whatever, it'll take that into account and show you how that's going to fill and pack. Now another one that we're looking at, and again, this is one of those advantages of running a simulation beforehand, is looking at the pressure gradient, right? So typically what you're hoping for is a constant pressure gradient, which is the pressure drop per unit length. So you're looking for that to be fairly constant, or you're looking for the pressure rise to be fairly uniform, right? Until of course you see that little spike at the end, because the flow front keeps getting smaller and smaller. But if you're going to see spikes through the flow, then that's usually a problem, right? That means you have some fixing to do. There's an issue with some of the molding parameters, or the issue with the
Yeah,
design.
it's one of the key things to result interpretation, which is our last session, is like uniformity. And why are we concerned? Literally, when you have different pressures, especially large spikes like you're indicating, Nikhil, or varying temperatures, right? There's going to be different cosmetics and different physical properties. And that variation is the root cause of most of our evils. If we can minimize that variation, there's, reduction in risk. And some of these are more obvious than others. When you get a large spike like this, what's going to go on in these last places to fill? You're certainly starving it as far as effective pressure and things along those natures. But yeah, balance, uniformity, symmetry, some of the key things we like to see.
Yep, definitely, and again, to that end, if you're looking at, say, the cross sectional flow, then in this case you see that you've got one rib that's filled and the other one that's not. That is uh, that's not ideal, right? If you've got something that is symmetric, then you would hope that they're being, or you would expect they're going to be filled at the same time. And if they're not, then maybe you've got to play around with your injection location a little bit. Now you do see some of these artifacts that we mentioned previously as well, one of the big ones that is really something that's really difficult to avoid is a weld line or a meld line, right? A weld line is essentially when you've got two flow fronts meeting head on. A meld line is when you have these two flow fronts meeting and they flow in the same direction subsequently. So, like I said, these are quite hard to understand. But having said that, quite hard to avoid. But having said that, it is important to be able to predict where they will appear and where they will form. And typically, these weld lines tend to be the areas where the part is quite weak. So, going back to what we talked about earlier with um, just running a regular FEA of the CAD model versus running an FEA of the as manufactured, as molded part, this is where something like that comes in, right? So you can actually analyze the stresses, analyze the strength of the part at the region of the weld line, and that will give you a better idea of the strength of the part. Now you've also got things like hesitation effects, right? So uh, it is exactly what it sounds like. The flow front kind of hesitates to flow through a certain region. The reasons for that may be varied. It could be your geometry, it could be your gate location, it could be a combination of a lot of different things. One common way to fix it, of course, is going back to our first design principle, which was uniform wall thickness. So you'll see as we go through this that a lot of these um, issues that we see, a lot of these artifacts that we see, can actually be traced back to some of these design principles that were either violated or just simply not followed correctly, right? There's some uniqueness, some um, proprietariness, I suppose, to the design that causes it to behave slightly differently. But then again, you use Moldflow to fix that.
Yeah, one of the interesting things about that is the stall, drops the melt temperature and creates a higher viscosity. So it's a domino effect. And if you still today, there's a a great chance that someone might choose to put the gate near that hesitation
Yeah.
to try to force it in there, but you just aggravate that hesitation, ironically. To your point, Nikhil, like where you place that gate and start building that mold is, a built-in iteration in order to compensate.
Yeah, absolutely. Now, avoiding underflow. This is again a pretty big one, right? Especially when you've got components like this. Essentially, what we're looking for is we want the velocity, the flow lines, the flow direction to be perpendicular to uh, the fill contour lines, and anything that's not perpendicular, again, you'll tend to see issues with that, right? You'll tend to see formation of artifacts. You'll start to see formation of weld lines. So in this particular instance, you see the weld line, instead of being a line, actually starts moving inside the already frozen layer. So
Sometimes that can actually, benefit as far as washing out the weld line or improving the strength. In other cases, it can cause like distortion through the thickness. So kind of an interesting phenomenon, but truly, you're seeing like what I like to refer to as my superpower with MoFlow is that X-ray vision to see what's going on, beyond that surface level to
mhm.
actually look at the internal aspects of these flow dynamics. It's always still amazing to me as far as compressible flow and how complicated it is when you start looking inside.
Absolutely, yeah. What you see on the surface is never what's going on inside, right? And as a analogous to that would be if you're looking at flow through a pipe, the velocity against the wall is actually going to be zero. The highest velocity is going to be through the middle. So unless you're analyzing what's happening through the middle of the pipe, you're not really getting the full picture of what's going on there. flow leaders and deflectors. Again, this is another one of those things that firmly falls into the um, into the principles and not rules, regard the guidelines and not rules category. So we talked about uniform wall thickness. Well, we could have leaders, we could have deflectors, right? Where you have subtle increases in thickness or subtle decreases in thickness. What
Great
that
example of violating the design guideline is uniform wall, but it's an intelligent approach to distributing the pressures. So you get uniform pressures or flow front progressions that don't like backfill like this air trap. And so bringing that to the design, the part design, is a huge advantage. These integral gating built into the part design or flow leaders, flow inhibitors. That's when you take a look of, like I do, tear things apart and you see a plastic component that has these things built into it, you know that that's a good designer who thought that through.
Yep. Now this is another one where you've got the molecular orientation kind of actually being impacted because of the flow. Now, again, this is something that we can talk about in quite some detail. We will spare you that for now. But if you do want to get more information on this, again, feel free to reach out to us and we can talk about this in depth. Now this is a big one where you want all of these molds to be filling at the same time, and that is the principle of flow balancing or runner balancing. Um, Now this can lead to a whole bunch of different issues by itself, a whole bunch of different complexities, right? As you can see on this particular image on the left, you can quite clearly tell that the ones further at the back or the ones closer to the top of the picture, they definitely take a lot longer to fill than the ones at the bottom of this or the picture on the left, right? On the right, though, you see they're a lot more even. They're a lot more uniform. There's a um, 4 thousandths of a difference in 4,000 of a second difference in how long it takes to fill. And that's okay. That's fairly negligible, as opposed to say 4/10 of a second. Now, again, you need the runners to be large enough that there is, actual heat in the runner, right? You want the part to be the part temperature to be optimized, and you want to make sure that you can actually control the heating in there that goes through the runners. Now, similarly, you're looking at how quickly the runners are freezing with respect to the part, right? You don't want that to be a barrier to having identical parts, to having identical molded parts. Now, similarly, again, we're looking for all of this, by the way, relates to runner balancing, right? So if you're looking at um, multiple identical parts, designing them all at once, then absolutely you do need to consider all of these different factors. And in any case, it's definitely good to have this information about fill time and flow rates. Just because you're molding one single part doesn't mean, for example, that you need to that you should ignore, say, the frozen layer ratio, etc.
Yeah, and we'll touch on that next session
Yep.
for sure. But there's a lot of complex issues that go into optimizing feed systems. It boils down to, what are your goals? What's your quality criteria for the component? Um, the material itself, how sensitive that may be to share imbalances, or material residence time, degradation. There's no easy button. And we'll touch a little bit more on that in the next session, but just as much thought, I guess one of the messages should be put into the feed systems and the cooling systems for our molds when we get to that point.
Yep, definitely. Yeah, as Brian said, we'll definitely touch on some of this stuff in the next session, next two sessions actually. Okay, so this one's a fairly obvious one. Shrinkage. We want the shrinkage to be predictable. Just if nothing else, to be able to understand what the allowance in your mold should be, right? So this one's fairly simple, fairly self-explanatory. And again, some of these things we'll talk about going forward as well. Shear stress. Again, this is a huge one. The shear stress during the fill has to be less than the critical level. If not, then there's a whole bunch of issues that pop up just as a result of that. Similarly,
Just one
cooling.
comment about that too, in regards
Sure.
to limit. Again, these are guidelines, and
Yep.
and just a comment in regards to this may, be a starting point, but say if it's a sensitive cosmetic part, this limit could be a lot higher. Or if it's an easygoing material, say like polypropylene, we know in living hinges, this value is going to far exceed this limit. So again, you're just going to keep the application and material in mind, and what the quality criteria is.
For sure. Similarly, this is another one of those fairly self-explanatory principles. You want cooling for the entire molded part to be uniform, fairly uniform at least, right? And if you have non-uniform cooling, things tend to bend and warp in a way that tends to become unpredictable, right? So always keep in mind you want the cooling to be as uniform as possible, and especially in structures like this, when you've got box like structures, you will see that the walls will tend to kind of bow inwards, almost bend inwards, and it doesn't look like a box anymore, right? It just looks like a shape of an enclosure that may or may not be straight. So for something like this, especially as you get bigger and bigger in size, it can be fairly important to see that the cooling portion of this, it remains uniform. All right, so to summarize, this was, of course, session 2. What we talked about mainly, what we focused on mainly, was upfront part design. So how do you kind of make these decisions early on, right? What are the principles, what are the guidelines that you would keep in mind before we made these decisions about part design going in? Now, again, we did talk a little bit about materials as well. Overall, though, it's really hard to kind of divorce these from each other, right? Just to separate all of them. So a lot of the principles that we saw with part design, we are going to use in session 3. The big one next time around is process development, mold development. How do you validate the mold design? How do you do a virtual design of experiments, for example, to identify what the biggest, the most influencing parameter is? So that's what we'll talk about next time around. But if you have any questions right now, feel free to type that into the chat window, and we will be happy to answer them.
We actually left enough time for questions this week.
We did, yeah. We have about 5 minutes for that. So just give you guys a couple minutes here to type in any questions you may have, and also anything else that you might want to see in here, right? So, for example, in the next session, if you had any questions about what we're doing next session or next time around, or anything that we did this time or even last time for that matter, feel free to let us know. And by the way, you should see a few links in the chat window already. So there's one for the remote work resources page that I pulled up earlier. There's also a link to the part one, Plastics 101, and there is another link to a webinar about Granta, the material database, the ANSYS material database that we talked about a little earlier as well. Okay, so it looks like we don't have any questions here. Well, in that case, thank you all for joining us. Stay safe.
Yeah, thank you.
Yeah, hope to see you all on the next session, which is going to be in about 3 or 4 weeks time. You will receive, by the way, an email since you are signed up to this session. You will receive an automatic reminder email just before your next session, letting you know the date and the time and everything. So thank you all for joining, and hope you have a great rest of the week, and stay safe. Thank you.